Bismillahirrahmanirrahim. Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today we will be presenting about topic 5 for air conditioning and refrigeration, code Dju31012 heat exchange. Our lecturer is Puan Mahani binti Muhammad Zamri. My name is Muhammad Naufal bin Alias. My matrix number is 01DPU20F1019. Okay, let's go on with the introduction. Okay, what is heat exchange? Heat exchange is basically a device or equipment designed specifically for exchanging heat. Heat exchange is an important unit operation that contributes to efficiency and safety of many processes. The medium to exchange heat is basically fluid in the form of liquid or air. The fluid may be separated by a solid wall to prevent any mixing, or they may be in direct contact. The history of heat exchange turns back into 1923 when a person named Dr. Richard Seligman, as shown in the picture beside it, invented the plate heat exchanger, or in acronym PHE. This invention revolutionized methods of indirect heating and cooling of fluids. The plate increases the heat exchange efficiency and made an impact on heat exchange industry. The application to heat exchangers are used in many industries, such as oil and gas, power generation, and others for heat transfer. The most well-known type of heat exchanger is a car radiator. So, on to the classification to heat exchanger. The classification to heat exchanger, since these fluids can be gases as well as liquids, a classification needs to be made. The four basic classification of heat exchanger. The first is fluid path, the second is state of medium, then construction, and finally about surface compactness. Forgive about that. Okay, let's go on with the first one. Okay, this is fluid path, parallel flow. In heat exchange, parallel flow, two fluids enter the exchanger. As seen, these fluids enter the exchanger at the same end and travel in parallel to one another to the opposite end. And there is the example of how parallel flow travels. And then there is a graph of how basically it is shown, it is described. Okay, then the next one is, then there is a counterflow. Counterflow is the completely opposite to parallel flow heat exchanger. The fluids enter the exchanger from a different opposite, one on the other end and the other is on the other end. Okay, then it is the same. The graph is described, just the path of the line is different. Then there is the cross flow. Cross flow is a bit different than parallel flow and counter flow. Cross flow is different as the fluid travel roughly perpendicular to one another through the heat exchanger. Then I will pass the second to my colleague Muhammad Fadil. You may continue.
My name is Muhammad Fadil bin Abdul Hamid. My metric number 01DPU20F1023.
Sorry about that.
Alright, state of medium. The second classification made in depending on the state of the media in the heat exchangers. First, liquid to liquid. Exchangers are tools in which two liquid interacts. Next, gas to gas. Also, heat exchangers like air preheat in steam plant and helium-cooled reactor gas turbine plant have to be mentioned. This device operates with heat transfer coefficients that are between and 100 times lower than coefficient of liquid to liquid exchanger. Gas to gas exchangers are general much larger and heavier if a same amount of transferred heat is demanded. The third type, the liquid to gas heat exchange or vice versa, usually water air are used of instead in automatic reactor. Next, construction. There can be many variations on the shell and tube design. Typically, the end of each tube are connected of plume, sometimes called water box, through hole turbine tube sheet. The tube may be straight or be in shape of U-tube. In nuclear power plant, called pressurized water reactor, large heat exchanger called steam generation are two-phase shell and tube heat exchanger which typically have U-tube. They are used to boil water, recycle from a surface condenser into steam to drive a turbine to produce power. Straight tube exchanger, surface condensed power plant of often one pass straight tube heat exchanger. See surface condenser for diagram. 2 4-pass design are common because the fluid can enter the exit the same side. This makes construct much simple. They are often better direction flow through the shell. Fluid does not take a shortcut through the shell side, leaving effective low flow volume. There are generally Higgins log mean temperature difference between the hot cold steam. Many companies, however, do not use two-pass exchanger. Often, multiple heat exchanger can be used simulated in counter current flow, a single large exchangers. Next, plate heat exchangers. It is composed of multiple thin, slightly separated plates that have very large surface area and fluid flow passage for heat transfers. The plates are often spaced by rubber sealing gaskets, which are cemented into sections around the edge of the plate. The plates are pressed from through a right angle to the direction of flow of the liquid which run through the channel in the heat exchangers. Next one. Oh, balik. Aku tinggal satu. Okay, next, spiral heat exchanger. A spiral heat exchanger may refer to a helical coil, the configuration, efficient use of space. They can easily clean. A spiral heat exchange or SHE is a coil tube arrangement with two-channel coil one around the another. These two channels operate in counterflow arrangement, offering excellent turn-down ration while optimizing flow pattern, which in turn exchange heat transfers. Next. Regenerative heat exchangers. Next part. A regenerative heat exchanger, or more commonly, a regenerator, is a type of heat exchanger with heat for the fluid intermittently stored in thermal storage medium before it is transferred to the cold fluid. To accomplish this, the hot fluid is brought in contact with the heat storage medium. Then the fluid displaced with the cold fluid which absorbs the heat. In regenerative heat exchangers, the fluid on either side of the heat exchanger can be the same fluid. The fluid may go through internal processing step and then is followed back through the heat exchangers in opposite direction for further processing. Usually, application will use process cyclically or repeatedly. Next. Next one. Surface compactness. For compact surface, the surface area density is more than or equal 700 meter per m. And for non-compact surface, the surface area density is less than 700 m2 per m. Each individual particle on the surface on an object is invoked the heat conduction process. An object with a wider area has more surface particles working to conduct heat. As such, the rate of heat transfer is directly proportional to the surface area through which the heat is being conducted. Next to Ashwat.
Okay, thank you, Fadil. My name is Muhammad Aswad bin Mazlan. My metric number 01 DPU 20F018. So I'll be talking about the logometric mean temperature difference, or also we can call as LMTD. The logometric mean temperature difference is used to determine the temperature driving force for heat transfer in flow system, most notably in heat exchange. The LMTD is a logometric average of the temperature difference between the hot and cool feed at each end of the double pipe exchanger. For a given heat exchanger with constant area and heat transfer coefficient, the larger the LMTD, the more heat is transferred. The use of LMTD arises straightforwardly from the analysis of a heat exchanger with constant flow rate and fluid thermal properties. As you can see, there is above a graph or a graph for LMTD. So the first is showing the counter flow graph. Okay, so second is a parallel current flow or parallel heat flow. So showing that there is a formula given down there, so we can use to find the the LMTD. Also, the third is a counter flow current, and it's given a formula for you to find MTD. Next slide. So this is the first formula for LMTD. So let me tell you what the meaning of the equation. Where TA is the temperature difference between the two steam at the NA, and TB is the temperature difference between the two stream at the NB. With this definition, the LMTD can be used to find the heat in a heat exchanger. So the Q equal U times A times LMTD, where is Q is the heat exchange, heat duty, U is the heat transfer coefficient, and A is a heat exchange area. Note that estimating the heat transfer coefficient may be quite complicated. This whole both for parallel flow where the steam enter the same end, and the counter flow where they enter from different end. In a cross flow, which is one system, usually the heat sink has the same nominal temperature at all points on the heat transfer surface. A similar relation between exchange heat and LMTD hole, but with a correction factor. A correction factor is also required for other more complex geometry, such as shell and tube exchanger with muffler. Okay, next slide. So this is an assumption and limitation for LMTD. It has been assumed that the rate of the temperature of both fluid is proportional to the temperature difference. This assumption is valid for fluid with a constant specific heat, which is a good description of fluid changing temperature over a relatively small range. However, if the specific heat exchange, the LMTD approach will no longer be accurate. The secondly, a particle case for the LMTD are condenser and reboiler, where the latent heat associated to phase change is a special case of the hypothesis for a condenser. The hot fluid inlet temperature is then equivalent to the hot fluid exit temperature. It has also been assumed that the heat transfer coefficient is constant and not a function of temperature. If this is not the case, the LMTD approach will again be less valid. The LMTD is a state concept and cannot be used in dynamic analysis. In particular, if the LMTD were to be applied on transition in which for a brief time the temperature difference had different sign on the two side of the heat of the exchanger. The argument to the logarithm function will be negative, which is not allowable. So the last one, steady state flow, no phase change during the heat transfer. Change in kinetic energy and potential energy are neglected. So that's next slide. So the conclusion for the presentation today, from the presentation, we can conclude that the heat exchange is not limited to transferring heat between fluid. It's important residence in various aspects. Type and size of the heat exchanger play an important role in the exchange efficient as well as the material. Heat exchange serves as the backbone of the industry in which it's used. So the arrangement of heat exchanger are very important. So that all from us. Thank you.
That is the end of the presentation.